Hello everyone. In this video, we are going to solve some additional problems from GATE. The first question is a 400 volts, 50 kilowatts, 4-pole, 50 hertz star-connected induction motor has a full load slip of 4%. So full load slip is given, and here 15 kilowatts is the output power of the induction motor, and P is the number of poles, and 50 hertz is the supply frequency, and the motor is star-connected. Okay. So we have to find out the output torque of the machine at full load. So we have to find out the output torque under full load condition. So these are the options. First one 1.66 Newton meter. Second one 95.50 Newton meter, 99.47 and 624.73. Okay. So first we'll write the given data. Here the output power is given. So P out is equal to 15 kilowatts. So 15 into 10 power 3 watts. And number of poles given, P is equal to 4, and the supply frequency F is equal to 50 hertz, and the machine is star connected. So star connected induction motor, and then the full load slip. So slip corresponding to full load condition, SF be the slip corresponding to full load condition 4%, 4 by 100, so 0.04. So now we have to find out the torque corresponding to full load condition. That is the output torque corresponding to full load condition. Okay. So the torque can be written in terms of the power output as P out divided by omega. Okay, P out divided by omega. So omega is nothing but 2 pi n by 60. So where n is the speed of the motor. So n is equal to 1 minus, so this n will be corresponding to the full load condition. So we are going to find out the torque under full load condition. So the speed will be equal to the full load speed. So 1 minus S full load into NS. So this is a slip corresponding to full load condition, and this is NS, which is a synchronous speed. So first we will find out NS because SF is given. So NS is equal to 120 F by P. So 120 into 50 divided by 4. So on simplification, we will get 1500 RPM. Okay. So now we'll substitute NS value in any equation so that we'll get the speed corresponding to full load condition. So 1 minus 0.04 multiplied by the synchronous speed 1500. So this will be equal to 1440 RPM. Okay. So now we'll substitute in the torque equation. So torque corresponding to full load condition will be equal to 15 into 10 power 3 divided by 2 pi into 1440 divided by 60. Okay. So on simplification, we will get 99.5 Newton meter. Okay. So the answer is C. The second question is a 3-phase squirrel cage induction motor has a starting torque of 150% and a maximum torque of 300% with respect to rated torque at rated voltage and rated frequency. Okay. So here the starting torque and the maximum torque are given as a percentage of the rated torque. Okay. Rated torque is nothing but the full load torque. Okay. Now next one, neglect the stator resistance and rotational losses. The value of slip for maximum torque. So now we have to find out the slip corresponding to maximum torque, and these are the options: 13.48%, 16.42, 18.92 and 26.79%. Okay. So first we'll write down the given data. So first the starting torque is 150%. Okay, starting torque is 150% of the rated torque. So rated torque is nothing but the full load torque. So 150% of full load. Okay, 150% means 150 divided by 100. So that can be written as 1.5 into full load torque. Okay. Similarly, the maximum torque is also given. So the maximum torque is 300% of the full load torque. Okay, rated torque means full load. So 300 by 100 will be equal to 3. So 3 into torque corresponding to full load condition. So if we divide these two equations, we'll get TST by Tm is equal to 1.5 T full load divided by 3 into T full load. So full load torque will get cancelled. So 1.5 by 3 is 1 by 2, which is equal to 0.5. So the ratio between the starting torque and maximum torque is equal to 0.5. So it is given. So now we have to find out the slip corresponding to maximum torque. So we have already derived the ratio between starting torque and maximum torque. So which is equal to 2 into Sm divided by 1 plus Sm square. So where Sm is the slip corresponding to maximum torque. So from equation 1, this is equal to 0.1. Okay, ratio between starting torque and maximum torque is equal to 0.5. So on cross multiplication, we'll get 2 into Sm is equal to 0.5 plus 0.5 into Sm square. So on rearranging, we'll get 0.5 Sm square minus 2 into Sm plus 0.5 equal to 0. So on rearranging the above equation, we'll get quadratic equation in Sm. So on solving this quadratic equation, we'll get Sm is equal to 0.2679. So which is equal to 26.79 percentage. Okay. So the answer is D. Now the third one, 400 volts, 50 hertz, 30 HP. So this is a motor rating. Three-phase induction motor is drawing 50 ampere current at 0.8 power factor lagging. Okay. So the line voltage and line currents are given. The stator and the rotor copper losses are 1.5 kilowatts and 900 watts respectively. So this is the stator copper loss and this is the rotor copper loss. Then the friction and windage losses are. So friction and windage losses means mechanical losses are given. So 1050 watts and the core losses are 1200. So this is a core loss. This corresponds to stator core loss because in the rotor we have only copper loss and the core loss is negligible. So now we have to find out the air gap power of the motor. Okay, air gap power of the motor will be, so the options are 23.06 kilowatts, 24.11 kilowatts, 25.01 kilowatts and 26.21 kilowatts. Okay, so first we'll write down the given data. Here the air gap power means the air gap is present in between the stator and the rotor. Okay, so the power present in between the stator and rotor is nothing but the input power given to the rotor, that is P2. Okay, so we have to find out the rotor input power. Okay, now we'll write down the given data. So we'll write down the rated voltage, there is a line value. So 400 volts, the supply frequency F is equal to 50 hertz and the current drawn from the supply IL is equal to 50 ampere and the power factor cos phi is equal to 0.8. So this power factor is lagging. And then the rotor copper losses, stator and the rotor copper losses. So stator copper loss is equal to 1.5 kilowatts and then rotor copper loss, okay, equal to 900 watts. So friction and windage losses are given. So friction and windage losses are nothing but mechanical losses. So mechanical losses is equal to 1050 watts and then core losses are. So as I said earlier, this core loss refers to stator core loss. Okay, stator core losses is equal to 1200 watts. So now we have to find out the air gap power, which is nothing but the rotor input power. Okay, so the input power to the rotor can be written as input power to the motor minus the stator losses. Okay, so the stator losses includes both the stator copper loss as well as the stator core loss. Okay, so this is given. So now we have to find out the input power. So input power can be written as root 3 into VL IL cos phi. So this is a power input given from the three-phase AC supply to the induction motor. Okay, so we have VL value, IL value as well as the power factor. So on substituting all these values, we'll get the input power. So root 3 into 400 into 50 into cos phi is 0.8. So unless or otherwise specified, we have to consider these values of voltages and currents as line values. Okay. So on simplification, we will get 27,712 watts. Okay. So next we'll find out P2. So P2 is equal to 27,712. Okay, P in value minus the stator losses. Here the stator losses includes both stator copper loss as well as the stator core loss. Okay, so stator copper loss is 1.5 into 10 power 3 watts plus core loss is 1200 watts. Okay, so on simplification we'll get 25,012 watts. So which is equal to 25.012 kilowatts. Okay, so the answer is C. So now the fourth question is a three-phase 50 hertz 6-pole induction motor has a rotor resistance of 0.1 ohm and reactance of 0.92, rotor resistance and rotor reactance. Neglect the voltage drop in stator and assume that the rotor resistance is constant. Okay. So given the full load slip is 3%, full load slip is given, which is 3%. We have to find out the ratio of maximum torque to full load torque. Okay, the options are 1.567, 1.712, 1.948 and 2.134. Okay, so first we'll write down the given data. So the supply frequency F is equal to 50 hertz and the number of poles P is equal to 6. The rotor resistance R2 is equal to 0.1 ohm and rotor reactance X2 is equal to 0.92. And then full load slip. So full load slip is 3%, 3 by 100. So that is equal to 0.03. Okay. So we have to find out the ratio between the maximum torque to full load torque. Okay. So already we have derived the formula for maximum torque to full load torque ratio. So which is given by Tm by Tfl is equal to Sm square plus Sf square divided by 2 into Sm into Sf. So where Sm is the slip corresponding to maximum torque and Sf is the slip corresponding to full load torque. So Sf is given 0.03. We have to find out the slip corresponding to maximum torque. So the formula for slip corresponding to maximum torque is R2 by X2. So which will be equal to 0.1 divided by 0.92. So on simplification we will get 0.1086. Okay. So now we'll substitute both Sm and Sf in this ratio. Okay. So let this be equation 1. So we'll substitute both Sf and Sm value in equation 1. So we'll get the ratio of maximum torque to full load torque. Okay, that will be equal to 0.1086 whole square plus 0.03 whole square divided by 2 into 0.1086 into 0.03. Okay. So on simplification, we will get 0.0127135 in the numerator divided by 0.0065214. Okay. So which will be equal to 1.9495. So this is the answer I am getting. So the option is C, 1.948.